to part 2, chapter 7. So a reminder, homework, activity 3, and office hours are a great place to talk about any of that. Homework, activity 3, quiz 4 that's coming up, grades from quiz 3, exam 2. See me in office hours to do that. Okay, so I mentioned part 1, chapter 7 is really introductory. If you've been doing the lab activities at Miramar, or if you recall CHEM200Ch7p2, that was probably a lot of review. Now we'll go in a little bit more detail, limiting reactants. This excess reactant type problems for sure are a little more difficult over the years for students, so we'll talk about that. And then it really just ends on kind of a random summary of 3 classes of reactions: combustion, the alkali metals, the halogens. So really encourage you. This was a busy week, quiz, activity, new lecture material. Next week is coming with the exam. All right, so this is where we left off. We had grams of something and grams now we can see of something else, okay? And what we're going to see here is how many grams of nitrogen, that's what's being asked for, are produced from 6 grams of sodium azide. So again, I'll try and put in the path here. That's grams, moles, mole conversion, and then grams. So in this case, we're starting with grams of sodium azide here. That means you need the molar mass of sodium azide here to get to moles of that. Then you need the mole ratio, and that's 3/2. So we're going to nitrogen. 3 needs to be on the top, 2 needs to be on the bottom. And then we need the molar mass of nitrogen. Don't forget it's a diatomic. Include that. And you should be able to get the grams, 3.88 for nitrogen. Okay, so that's grams, moles, grams. Okay, so another example of that, decomposition of 100 grams. This is a lead-4 oxide, and we're looking for grams of oxygen. So same kind of setup. If you take a look, this is molar mass. That gets us to moles. And the mole ratio comes from the balanced chemical reaction. In this case, it's 1/2 because we're going to oxygen. And again, diatomic means we have to account for that molar mass of oxygen to get grams of oxygen. So this is a really similar path, grams, moles, grams, that we've been talking about. So now what we're going to see is we can scale this up a bit, okay? So stoichiometric mixtures. This was if the world was all right and perfect. Everything goes exactly as planned. All the reactants fully get used up. So if you take a look, this is a 1-to-1 ratio of methane water. So whether it's 1-to-1, 2-to-2, what do we got here? 7-to-7, all of it works out just perfectly. The ratio is 1-to-1. Everything gets used up to form these products. Okay, so that's a stoichiometric mixture. Well, again, this is reality. Usually, you have something left over. Okay, so the hydrogen and carbon monoxide are formed, but then you also have some leftover water still in the reaction mixture. Okay, so this is not a stoichiometric mixture. So that's this non-stoichiometric mixture that we're looking at now. So what's going to happen then? Of course, these are going to react. Okay, that's what this says. Methane and water are going to react, and they're going to form products. Okay, so 3 hydrogen molecules, 1 carbon monoxide molecule. Okay, so everywhere we had a stoichiometric ratio, those react. But then, of course, we have this. Well, you can imagine if you're wanting to purify your product, if you just want product, now you got to find a way to get rid of all of this. Okay, so this actually, I did a lot of synthesis in graduate school. That's the problem. That's the challenge, is purifying. You can get things to form, no problem, but can you get pure samples of that to form? That's a real challenge to do. Okay, so these questions now are going to be about non-stoichiometric. So what happens when we have these kind of scenarios? Okay, maybe you recall these are limiting reactant problems. So you have one reactant that's going to run out and it's going to limit how much product is formed. Our last example, the water, was the excess reactant. There was plenty of that. You had bits left over. In this case, the limiting is going to fully react. So limits the amount of product. And what this means, makes least amount of product, is when you do calculations, these are theoretical calculations, that's going to be the smaller number. Okay. And if that's making the smallest one, mentioned just earlier with that water example, the other reactant is going to be the excess reactant. So it's really important to feel comfortable with this terminology and to do the calculations and say, I know which reactant is limiting, I know which reactant is in excess, and we'll get to more about the yields here shortly. So here's what we're going to do. Find the limiting reactant, and there's three ways that I'm going to present. And for sure, if this was Chem 152, I tell my students, do this right here. Go to the amount of product, okay? If it's the question's asking for grams of product, just take both reactants, convert to product, and then you can figure out from there. That's, I would think, the easiest way. Well, you might want to do a lot of things other than just figure out the product, though, especially in Chem 200. So you may want to compare the amount of the second reactant needed to react with the actual amount of the first reactant. So now you're doing stoichiometry between reactants. You're not going straight to the product, which maybe you're used to doing. The examples earlier in these slides were going from reactant to product, product to reactant. So I want you to feel comfortable going from anything to anything else in the chemical equation. You might compare the mole ratio. Okay, so this is another way to see, is it a stoichiometric ratio? Is it the correct number that we're supposed to have? Is one more than the other, and which is it that's in the excess or limiting? So we'll start with moles. So again, this is how we started chapter 7. We're just doing some simple mole calculations. But in this case, if you take a look, it wants moles of product, and it's moles of reactant, and another moles of reactant. So right away, this should be red flag. This is a limiting reactant problem. As I mentioned, if I was Chem 152 telling you, I would say, well, take this all to the product. Okay, so if we take a look, silicon forms 0.4 moles of product. That's through the mole-mole ratio. Nitrogen forms 0.5 moles of the product. Okay, so the math here is just showing our mole ratio, but now it's the concept. Okay, so if we look here, we saw this earlier, this is less of amount than this. Okay, what this is telling us is this is not possible to form. I know you have enough nitrogen to get to 0.5 moles, but you don't have enough silicon. So this is not going to form. Get this out of your mind. Okay, and that tells us that the silicon is the limiting reactant. Okay, that's the one that runs out. 0.4 is less than 0.5. If that's the limiting reactant now, this is what it also tells us. That's going to run out, and theoretically, this is the maximum amount that we can form. I hate that terminology, but okay. What I just said was this is the maximum 0.400 moles that can form. But if you heard me earlier, I said the reason we chose 0.400 is because it is less. I think that's confusing. So really important, work on the terminology. What is the limiting reactant? It's got to be one of these on the left side. Remember, those are the reactants. And whichever the limiting reactant, then you can do the calculation to get to your theoretical yield. So go for it. Another one, 35 grams of nitrogen reacts with 12.5 grams of hydrogen. So this is your balanced chemical equation. Calculate the mass of product. Calculate the mass of ammonia. So if we're in grams, then remember our roadmap is just going to be grams, moles to grams, and you do that for nitrogen, but this is 2 reactants. You also do that for hydrogen. Okay, so do those calculations. You should come up with 2 values in grams, and then You got numbers. That's where you have to know the concept. The lesser of the number, 42.6, that's your theoretical yield. That's the amount ammonia that in theory could form from this combination. Can't have more than that. All right, so now we're going to go over the other ways to do these calculations. So if you look, how many grams of hydrogen, so this looks like a very similar problem, grams of hydrogen, and you're given grams of reactant and grams of reactant, okay? But take a look at the question. How many grams of hydrogen? And this is guiding you, what is the limiting reactant? So it's already telling you, this is the limiting reactant, beware, okay? So a couple things you can do. If you start, we want in moles, okay? So if we calculate, these are the moles of aluminum and moles of the HCl. And now if you take a look, what I've done here is I've showed you the mole ratio between HCl and aluminum. So I'm not going to the product, I'm showing you there's another way. So if you do this, 1.21 moles of aluminum requires 3.63 moles of HCl. That's what's needed, okay? If you go over here, what's needed is greater than what's actual, so our HCl is the limiting reactant. So if the question just stopped there, what's the limiting reactant? Here, this is a good way to do this problem. I'll compare reactant to reactant and realize HCl is the limiting. In this case, it did go all the way to hydrogen, so now I know I only have to do one stoichiometry problem, moles of HCl to moles of hydrogen to grams of hydrogen. So that's one other way to do this. Okay, so if we take a look, this might look familiar. Oh yeah, it's the same problem, okay? Grams of hydrogen, what is the limiting reactant? Take a look here. If we look at the mole ratios, that's 6/2. So what I'm looking at is 6/2 is a stoichiometric ratio of 3. Okay, so the numerator is HCl, the denominator is aluminum, and we calculated our moles earlier, and that's 1.25 moles of HCl over moles of aluminum. This equals 1.03. It does not equal 3. So again, that tells us, this is another way to determine, HCl is the limiting. So if you do that, you just have to do one stoichiometry problem, HCl to then grams of hydrogen. So that's two scenarios giving you another way to do this, determining limiting reactant from stoichiometry. So let's take a look at another problem here. How many grams of iron are produced when grams of aluminum react with grams of iron 3 oxide? Okay, so you need a balanced chemical equation. Then you need to choose the method that you want. I just provided you 3 methods to get to this. What is the limiting reactant? And then calculate grams of a product. So go ahead and pause the video, choose the method that you prefer. So this first one I'm going to show, again, takes us to moles of reactants. And I went to then moles of aluminum to how much will that react with moles of iron 3 oxide. So that's 2.493 needed. But remember, we don't have that. Okay, so that's our limiting reactant, the iron oxide, and now I can do stoichiometry based on that. So that's one way, again, comparing reactant to reactant, moles, and figuring out which is the limiting. Other option, same problem. Okay, again, maybe you did one of the methods I suggest, maybe you did another method. This method here, the stoichiometry is a ratio of 1/2 or 0.5. You could flip that if you want, 2/1. You just have to flip over here. And if you look over here, this does not get to that number. So we don't have enough iron 3 oxide, same kind of problem to get here. So basically what we're just talking about is strategy. What's your concept mapped? How do you want to approach these problems? Maybe these problems are really familiar to you and you feel good. Maybe you're interested in trying something new. So I encourage you, try those 3 methods. Come see me in office hours. We can talk about it if there's one that you prefer. So that's part of it. That gets us to limiting reactant, theoretical yield. Then we can evaluate how good was this reaction. Okay, this is very common in chemistry journals reporting. What's the % yield of this reaction? So the theoretical you calculated based on the limiting reactant. So we got to know the limiting reactant. This actual you would collect in lab, or you'd be given an amount, and you have to understand if it says this was actually produced, this was collected, that's your actual yield. And then of course we've got both yields, actual over theoretical multiplied by 100. Okay, let's be honest. Actual, if we're in a lab, we're spilling, maybe there's contamination. There's all kinds of things that can go wrong here that either contribute to a high % yield, a low % yield. So this is how we're doing to evaluate reactions. When I was doing synthesis, several reactions were in the 80 to 90% yield. It's fantastic, really great. And then a couple of times I would get 20 to 30 on different types of reactions, and it was super frustrating. All right, so let's take a look here. We have 1.55 grams of lead 2 nitrate, so that's a reactant. And this is not a limiting reactant problem. It tells you this Ki is in excess, so we could care less about the Ki. Then it says the precipitate was formed and collected. Right away, this should be red flag. This is an actual yield. Okay. If we're asking about % yield, we have the actual yield. Then we need to use this to get our theoretical yield. So that's grams to moles, mole to mole of product, grams of product. That gives us 2.16 grams of lead 2 iodide, and then take the actual 2.01 over the theoretical 2.16, and look at this, 93%. Fantastic. Okay, so that's identifying the pieces. Theoretical yield comes from limiting reactant. Actual over theoretical gives you %. So now let's put all this together. We have 9.05 grams of ammonia, and we have 45.2 grams of copper 2 oxide, and this is what was made. Okay, if that's what was made, that's the actual, and once %. So you have to calculate theoretical yield, and you have 2 reactants, so you have to determine the limiting reactant. So go ahead, pause the video, and calculate the % yield for this problem. As you look at this, remember we have 3 methods to do this. So I'm just going to present one here, grams of ammonia to moles of nitrogen to this grams of copper 2 oxide to moles of nitrogen, and you can see I'm comparing the product now, nitrogen, and the lesser number, 0.189, is what's going to form, or is what's going to be the theoretical yield of what could form. So that's 5.29 grams. You didn't form 5.29 grams, you got 4.61 grams. So this combines it all of this limiting reactant, theoretical yield, and % yield. So one other type calculation I want us to do on this before we finish this is probably new. I don't teach this in Chem 152. Maybe some of you did. It's in the textbook in there, but it's more complicated problems. Oh, sorry, it's already showing. Calculate the mass of excess carbon. Okay, so this is telling you there's an excess reactant, that's carbon. And it's telling you that is the excess reactant, and that you have a mass of carbon, and you have a mass of this titanium 4 oxide. Okay, so this is a little bit different problem because we don't care about the products at all. We're not looking at yield, theoretical, actual, none of that. Okay, so what we need to do, this isn't too familiar, that's just a metric conversion. grams to moles, moles to moles, and you can get to kilograms of carbon, and that's the kilograms of carbon needed to react with this titanium oxide. Okay, here's the difference, here's the key. That's not what you have. If you look up here, you were given 28.6 kilograms of carbon. So you take what you were given, what you need, and now you can find the mass of what's left over, or the mass of excess. So there is not any new chemistry here. It's just we're staying on the left side of the arrow. Still grams, moles, mole-mole ratio, moles, grams. Nothing's new except this small accounting of addition, subtraction, saying, wait a minute, I don't have enough of the, I have too much of the excess. So we took what was, what you had minus what you need, and now that's your total for the mass of leftover carbon. So that concludes the stoichiometry. The next 3 slides are just talking about chemical reactions. Okay, so it's kind of an odd transition in the chapter, but that's the heavy quantitative piece. Now some qualitative chemistry. Okay, what you have is combustion reactions, and maybe you recall that's combining with O2, forming CO2 and water typically, but this is the big one. It forms heat. Okay, that's the energy that moves your car. That's the energy, if you're on a camping stove, that cooks your meal, or whatever provides you heat when it's cold out. So now we're going to really kind of focus on that. Chapter 9 is going to be a lot about heat. Okay, so this is now, we're writing this in saying this is important. Okay, combustion, add O2, form CO2 and water. That's a combustion reaction. You can look at a lot of different substances. These are very common with organic compounds, hydrocarbons like methane. The next class is the reactions of alkali metals. And I know electron configuration, I spent a lot of time on that. It has 1 valence electron and can give that up to get to the noble gas. So the reactions here then, the neutral metal combining with halogens form the ionic compounds. Classic example of that, sodium, chlorine, sodium chloride. This violently reacts, this toxic gas, and yes, this tastes so good, sodium chloride. Another example is if you took a piece of sodium and dropped it in water, that's a violent reaction that forms hydrogen gas that can ignite, and it forms the cation. So that would be the sodium plus, the potassium plus, and it forms the hydroxide. So it's a basic solution that you could test the pH. And as I mentioned, you can light that hydrogen gas. This maybe you've seen before in the lab, being able to do that. So that's exothermic, puts off a lot of heat. And the last one are the halogens. So some of these are going to look familiar. Electron configuration, 1 away. That means it wants to gain 1. And they're the most reactive of nonmetals. Typically, we think of metals being really reactive. This is nonmetals that are also reactive. And you look at this, metal reacting with a halogen, just like what we saw slide before, forming the ionic compound. So if it's an alkali metal, that gets to potassium bromide. If it was a calcium, it would be CaBr2. So that's the reaction of halogens. Another one is when it forms with hydrogen. So you see they're both diatomics, and it forms these hydrogen halide compounds, HCl gas or HBr gas. So this concludes chapter 7. Please see me in office hours if you want to go over any of this.